method of virtual force for beams. We will discuss this for slender beams. By slender beams, we mean beams which have long spans compared to the depth. Usually we say when the span is 10 times or more longer than the depth of the beam, then you call that beam a slender beam. The opposite of a slender beam is a deep beam, whose depth is not so small compared to the span of the beam, and those beams have a slightly different behavior. So slender beams, so we will discuss method of virtual forces for slender beams. Now in beams, the internal forces are shear force and bending moment, as we have been discussing. Now displacement due to shear deformations is negligible in slender beams. Of course not negligible for deep beams, but for slender beams this is negligible. So we only need to consider displacement due to bending deformations, because this is significant. This is the major reason for the displacement. Now this is something we derived, this is the general formula. This is something we have derived before. So unit virtual external load at A is the point where we want to find displacement due to real load, and then you need to sum up the internal work done. So internal forces due to unit virtual load times deformations due to real load. Now so this is the same thing. I've just reproduced this left hand side. On the right hand side I have replaced internal forces due to unit virtual load with bending moment due to unit virtual load, and these deformations are bending deformations. In trusses we replace this term by member forces. Axial forces in members are the member forces in truss, and the deformations was elongation or shortening. In this case it is bending moment and bending deformation. Now since in case of a truss this was a simple process, because of the fact that the member force, that the axial force in a member does not vary along its length. We have same member force for a given member. We have same member force throughout its length. It doesn't vary over the length of the truss member. And there was a simple formula for there's a simple way to calculate elongation, although we haven't discussed that. Dr. Shoaib will take that part, but so bending deformation, so this in case of a beam, bending moment is the internal force, and bending moment is not constant throughout the span of the beam. Bending moment of course varies along the span of the beam, and this is the reason you need to draw bending moment diagrams, because you need to show the variation of the distribution of the bending moment along the span of the beam. So we have different bending moment at different locations, and correspondingly we have different bending deformations due to at different locations along the beam. Now for that reason the best way to perform this summation is by integration. So we need to integrate the bending moment and the bending deformations. So just using the symbols as we did before, delta PA for the unit virtual external load at A, and dA is just the displacement that you need, and this is what I said is integrations, just summation, but this time it needs to be done in terms of integration, because M is a function of X. This is delta M. Delta M is the bending moment due to unit virtual load, so you would represent it by delta M, just as delta P is a unit virtual low external load. Delta Mx means that this is bending moment due to unit virtual load, and since it is a function of X, we are representing it as delta M as a function of X. This is not delta M multiplied by X. This is delta M as a function of X. And then bending deformation, again this is a function of X. This something varies along the span. We will see how to calculate bending deformation. So for slender beams, this discussion is about bending deformation. When the behavior is linear elastic, then the bending deformation, which is actually the curvature, bending deformation means curvature of the beam, is given by bending deformation equal to d theta by dx equal to mx over ei. You have just done this. Let me show you on this slide. You have done this in your mechanics and material when you were discussing double integration method. You have discussed these things. You have this, what is this term? You can write this down as dx by d theta equal not like this. You can write it down like d theta by dx equal to 1 over rho. Now 1 over rho is curvature. Rho is the radius of curvature, and 1 over rho is curvature. and this you have proved that this is equal to, and this 1 over rho is equal to m over ei. This is what we have done when deriving the bending formula, flexure formula. When you are deriving this formula in chapter in the flexural stresses, in the chapter of bending stresses, you have derived this. Okay, so I'm not going to discuss these derivations because these are not something I'm supposed to cover, but I just wanted to show you that the curvature in a beam represented by either d theta by dx r1 over rho is equal to m over ei. Now m is a function of x. Let me take you back to the formula. Yes, I'm sorry, this one. So d theta by dx is equal to mx over ei. This is to mean that m is a function of x. Okay, now if you go back and put in the formula for the bending deformation, we have replaced bending deformation in our formula by mx over ei. Now for finding vertical displacement, so in a beam we need to either determine a vertical displacement or a rotation at some point. The tangent to the angle of the tangent to the slope, tangent to the elastic curve, theta, which is something that you have already studied. So for finding vertical displacement VA, delta PA, this force needs to be a unit force, 1 kilonewton or 1 kip, and then this delta mx is represented by delta mvx, just to tell that this is due to application of a vertical force. All right. And for finding rotation at some point, let's say point B, delta PB, in that case we will call it delta PB, because that point, this is just the point where you apply this unit virtual force. In this case it would be a unit moment, a 1 kilonewton meter or 1 kip foot, and delta m as a function of x is represented by delta m theta as a function of x, just to tell that this is now due to application of a unit moment. So the same formula with just different representation. This is theta b, and this is just to distinguish it from the previous symbol. This is delta m theta as a function of x times m as a function of x over ei. Now here is the summary. So if this is a given beam to you, and this is the given loading for the beam, and you are required to, for example, determine vertical displacement at point A and also rotation at, let's say, point B, then this is just to tell you what do those parameters mean. VA is this vertical displacement, and theta A is this angle of the tangent to the elastic curve at point B. Now, for finding this VA, we will have to apply a unit vertical force at A, delta P equal to 1 kilonewton or 1 kip, whatever is the unit, and then we will find the distribution of the bending moment, delta M as a function of delta MVX, delta MV as a function of X, and for evaluating this thing, delta M theta X, we will have to apply a unit couple moment or a unit moment at the point where we want to find rotation. So then you will have to again find a distribution of the bending moment as a function of x. So it's very important to be able to write the distribution of moment as a function of x. This is all you need to know for solving these problems. So let's go and start solving some of the problems.